Hi everyone, good afternoon. So before we get started with the second part of the module, let me just introduce myself. My name, actual name is pretty long. Don't bother. You can just call me Rajesh or Rajesh Panikar if need be. So when you type emails, please be careful because this autocorrects to panicked. Okay, this R usually becomes D if you have autocorrect enabled. But it's okay, don't panic. Uh, you can just call me Rajesh for short. Okay, just don't bother with the rest of the stuff. And my email ID is rajesh@nus.edu.sg. Okay, the suffix is not u.nus.edu. That's for students. For staff, it's nus.edu.sg. My phone number is 6516 5253. So you can call me if there is something really urgent. And you don't have the time to really wait for a response through email. My office is at EE20348. So if you have any doubts or difficulties, please drop me an email and drop by my office. Okay, and I would be glad to discuss things with you in person, which is always much better than discussing longer stuff over email. And if you email me, please allow me some time to respond, like at least a day or so, because there are days in which I have things on from 9 to 9. So yeah, please do give me some time. Don't always expect that I will respond within like 2 hours or 3 hours. Might not be always possible. And I got my PhD from NUS itself in 2011, some time ago. And during my PhD, I had a very interesting metric number, A0010100W. I didn't ask for it. It was a good coincidence that all the modules that I teach are related to programming or digital systems. My interests are mainly in embedded systems and machine learning and related applications. So if you want to do some interesting projects in fields related to those, please do let me know. Okay, so with that, let's get started with the module. But again, before we get into the technical content, I suggest that you read some of the stuff that I have given in this wiki. By the way, this wiki is having a lot of information about the module. In fact, all the lecture notes are there in the wiki. Of course, some of them require some correction here and there, but by and large, all the stuff required for you is in the wiki. The assignment 2 will be posted there soon. Right now, it's not visible to you. And you can see the lab manual for this week as well on the wiki. Okay. So if you want to, read electronically, wiki is a convenient place you can go to read up all the stuff. Okay. Things are hyperlinked as well, so you can click and go to the appropriate places faster than you can in the printed notes. So you already have an idea of what EE2024 is. We in the first half of the module, we already saw how to program a microprocessor or a microcontroller at its lowest level, that is assembly language, right? And understanding assembly language is kind of important to understand how the processor really works. And even though assembly language is not widely used in industry, it is still used in some critical parts of the code. Like for example, you can see the source code of your Apple iOS. A substantial part of the operating system, especially at the lower level, is written directly in assembly language. It's open source. You can actually Google and see. Okay, and right now you are in a position to read and understand most of it because it eventually is ARM assembly language. There are some slight differences with the assembly language that you have learned in the first part, but still it's by and large the same, so you can even read and understand how your iOS works at the core. And it is also used in other safety critical applications or time critical applications like rocket control systems or critical parts of operating systems, etc., etc. You also saw Pincel and GPIO. What was Pincel? A typical commercial chip will have more than one function associated with a particular pin, because the number of pins is directly related to the cost of the chip. If you want to increase the number of pins, the cost will go up. And not everyone might be using all the pins. So manufacturers usually multiplex different functionalities onto the same pin. So you can decide which internal unit a particular pin is connected to by configuring pin cell. It is for pin function selection, right? And then we also saw one peripheral, the simplest of all peripherals, which is GPIO, general purpose input output, which is as simple as setting or clearing a particular pin, right? Writing a 0 or writing a 1. And it can also be used for input. So you can see whether the digital input given to a pin is high or low, simply by reading the pin. And how do you read or write those pins? By reading or writing the appropriate registers. So you have already heard about FIO set, FIO clear, FIO pin, etc., right? So that was the simplest of all peripherals. Now, in the second part of the module, we will look at more complicated and arguably more interesting peripherals, such as those which can be used to interface with accelerometers, gyroscopes, compasses, etc., etc. Okay, and a lot of other peripherals. And this is becoming more and more prominent right now because we are in the era of so-called Internet of Things, right? What exactly is it? It's just a system where you collect a lot of data from various sensors, which read the various physical parameters of the environment around it. It could be the number of vehicles passing through a particular road. It could be the temperature at a place, pressure at a place, whatever, right? And then this information is relayed onto some central server, typically some cloud-based server, which will do some processing and which will respond with something which will be used to change the environment, some response from the server, okay, which could be used to activate something, like for example, which could be used to control the red or orange or green lights that you have on the road, traffic lights. Yeah, or it could be something else. So these are essentially Internet of Things applications. And in the era of Internet of Things, this module is quite relevant. Okay, because this is probably the most relevant module when it comes to these kind of Internet of Things related applications. Of course, this module is not enough, not sufficient, but it is absolutely necessary, okay, for you to get into IoT related stuff. And if you look at the number of job opportunities, job openings out there, if you understand this kind of stuff well, there are a hell lot of options out for you. And I dare say E2024 or 2028 is the most industry relevant module that you will ever study. I mean, at least at a core level. Okay. And the contents are fairly state of the art. So the processor that we are using is a bit dated, I would say, because it was released somewhere in 2010 or so. But it is still not very different from the state of the art processors you have. Like this is based on ARM Cortex M3, which is still widely used in the industry. It is not considered obsolete by any means. And then there is Cortex M4, which is also widely used. In fact, a variant of Cortex M3 is used in your iPhones to collect sensor data. Apple calls it a motion coprocessor, which is a processor which is very similar to LPC17XX. In fact, in one version of the iPhone, I think it is iPhone 6s or something, the processor used is almost exactly LPC1769. It is 178 something, which is quite close. Well, these are information people get based on analysis of the chip. Apple wouldn't tell us any details anyway, right? Being a very secretive company. Okay, but having industry relevance comes with some disadvantages as well. It's not something you can just read off a textbook. It's something you can learn only by getting your hands dirty. This module is kind of like learning swimming. I can show you a lot of YouTube videos. Okay, and then if you just enter into a pool, okay, pool is still okay, you probably won't die. But if you get into real deep water, you might not really survive just based on YouTube videos that you watch, right? Same goes for learning this module as well. If you just try to follow whatever examples I show and say that, oh, I have seen sufficient examples, I'm good to go. No. You will feel that you are good to go, but you will not be able to survive in the real world. Okay, you will sink. The only way to learn is just do it. Just try it out. And when you try it out, things might not be always smooth, right? Learning swimming or learning how to ride a bicycle, etc., usually comes with some associated course. Most likely you will fall if you try to, or when you try to ride a bicycle for the first time. Same goes for swimming. You will struggle quite a bit, right? You will end up, drinking some water. And if it is in a public pool, you might end up, drinking not so nice water. But still, it's a part of the game. I mean, that's the only way you learn. Okay, so take it in the right spirit and be responsible for your own learning. I can only facilitate your learning. I can't really dig a hole into your skull and put the information in there and cap it. That's not possible. But that doesn't mean that you are entirely on your own, and that's what we are here for. We are here as lecturer tutors or teaching assistants in the lab or graduate assistants in the lab who will be able to help you out whenever you really run into trouble. But having said that, please don't just email me your codes and say, hey, my code doesn't work, can you tell me why? Okay, that is simply something I don't have the bandwidth to do, and I shouldn't be doing it. Because if I do it, I'm not doing you a favor. It's only when you try to spend your time, debug your mistakes that you learn. Anybody can write code, but not everyone can debug code. That's where you need knowledge, and that's where you get experience. Okay. So I will be very, very glad to discuss things at a higher level, but not really to the extent that I will have to look into your code line by line and figure out mistakes. That's simply something I wouldn't do. Okay. And ideally, you shouldn't ask anyone to look into your code. If you have any conceptual issues, if you think, if you are not sure whether you are doing it right, explain to someone, like for example, the teaching assistant or to me or to whoever, what you are doing, and then based on the discussion, try to figure out things. Okay, rather than expecting people to look through your code. And some do's and don'ts. Please attend lectures and tutorials regularly. You might think that, okay, all the materials are provided. Why do I have to really attend tutorials or lectures, right? Well, the fact is, yes, screencast is provided. It's not webcast, screencast is essentially the same thing. It will be recording whatever I am saying and whatever I show on the screen, not my face. I don't think anyone is too keen on my face anyway. So yeah, you will get to see what is going on in the class. But let's be realistic. If you skip lectures just because, well, screencasts are there, you definitely will be missing out on some of the experience. At the very least, if you attend lectures, everything will be over in like 1 hour 45 minutes. But if you wait for screencasts, well, personally, I don't have the discipline to spend 1 hour 45 minutes continuously watching a webcast or screencast. I'll get bored in 15 minutes, and then I will go to YouTube or Facebook. Okay, I'm pretty sure you will all do the same thing too. So eventually, for a 2-hour lecture, you will end up taking 5 or 6 hours for watching the screencast. And this discontinuity will cause some gaps in your knowledge as well. So it's better to just come for the lecture, be done with it. Keep your laptops closed, or at least don't go to, stuff other than lecture notes or related materials. Okay. And one request for people who have their laptops open, please do not play games or videos, etc., etc. Okay. If you really want to do that, you can go to the back row and play. Because if you sit in the front row and play, all the people behind you will be distracted. Okay, because anything which moves fast on the screen is bound to capture attention. Okay, so you'll be capturing their attention away from me and towards you, and that's not a good thing. And if you go to tutorials without really coming for lectures, again, you'll be missing out. And worst, if you don't go for tutorials, you'll be missing out even more, because tutorials are for more personalized interaction. So chances are that you'll be learning more in tutorials than in lectures in general. So yeah, please do not skip tutorials. Lectures can only introduce everything. You might not understand everything 100% in lectures, and that's only natural. Okay. So when you hear it all for a second time, and when you do some problems, things will really stick in your mind. And please come prepared for the labs. Okay, don't just go to the lab as if you are going for a movie. Please do go with some preparation so that you will be able to get more out of the lab. Okay, and lecture notes are meant to be only a rough guideline. Don't think of it as an encyclopedia which contains everything. So every now and then you might have to refer to other materials, like for example data sheets or tutorials, etc., to understand more about what you're doing. Okay, so don't expect to be spoon-fed. If you are expecting, or if I am spoon-feeding you, I'm not really preparing you for the real world, because once you go into the industry, no one is going to give you everything on a platter for you to eat readily. Okay, you will have to dig up information from wherever possible to understand things, to be able to do things. Okay, so take it in the right spirit, and take some responsibility for your own learning. And for a 4MC module, you are supposed to spend 10 hours. We have only 3 hours of lecture, so there is another 7 hours. And even after taking away labs, you are still expected to spend some time on the module. Okay, so please do spend that time to get the most out of it. And one very frequent comment that I get is, he's talking too many things, so we don't know what is required for the exam. So let me make it clear. My job is not to get you prepared for the exam. I am the one setting the question paper anyway. If my goal is to make you score well, I can always set an easy paper. But that's not the point, right? The point is to get you prepared for the industry, for the world. University is a place where you learn how to learn, not just to learn. Okay? So I might be talking about things which are not entirely examinable, which might not be relevant for the exam or from an exam perspective, but which are meant as pointers for you to explore more if you want to learn more, if you are interested in the topic. Okay, might not be for everyone, but then again, I can't please everyone in the class at the same time, right? Okay, so we will start with chapter 8, which is just an introduction to interfacing concepts. This is mostly left as a self-study, but I will still go through it very fast. But I expect you to learn chapter 8 from the notes or wiki to understand and appreciate things a bit more. Oh yeah, one last point. Some of you asked for slides. I'm sorry, I won't be giving the slides because slides are for you, for me to teach. Notes are for you to learn. Okay, so there is a difference, there is a distinction, but by and large, the contents are about the same. It is just that there is a bit more information and bit more explanations in the notes than in the slides. Okay, so notes are more readable than the slides, just that it is not in the bulleted form. So this is the picture of a generic computer system. A generic computer system consists of a processor core, microprocessor. Some people call it MP, some people call it mu p, the Greek letter mu, and some people just call it processor. Some people call it CPU. It's all the same, processor. And then we have a bunch of stuff around it, because processor is the brain of your system, but a brain without a body is not too useful. So we have a bunch of stuff around it to have a complete system, which includes RAM, which is your scratch pad memory, which is volatile in the sense that the contents will not survive a power down. So when you power down and power up, there is nothing left in the RAM. So it's volatile, it vaporizes. Then there is flash or some kind of a storage mechanism which is not volatile, where you typically store your program, because your program still has to survive a power loss, right? And most systems do have some kind of a system timer. Just like how most human beings have some kind of mechanism to check the time, right? Like for example, a watch, or these days you just check your time on the phone, right? But some kind of mechanism used to check the time. So that is your system timer. It's typically used by the operating systems, because in modern computers, you almost always have an operating system which will manage everything, right? So it is operating system which will decide how long a particular program is supposed to run. So for that, the operating system should have a sense of time. And that sense of time is provided by your system timer, which is your systic, if you have seen it in the demo program. Then you typically have an interrupt controller, which is a manager of all the interrupts in the system. We will be looking at it in a lot more detail in the next chapter. And then we have these so-called communication interfaces or controllers or peripherals, such as I2C, HDMI, Ethernet, USB, etc., etc. So USB is so that you can plug in a USB device, right? Similarly, HDMI or mini display, etc., are to plug in some kind of display or monitors. And similarly, Ethernet is to connect to another computer. And the connection could be even wireless if instead of Ethernet you are using, let's say, a Wi-Fi module. Then you connect to some other device without really using wires. And then for sensor devices, the most popular interface used is I2C, which is what we are going to learn very soon today itself. Okay. In chapter 8, we will be looking at I2C in more detail. And the exact connection between these so-called interfaces and the devices are dependent on the interface. So if it is USB, how many connections are there between the USB port and the USB peripheral or the USB device? Have you seen the USB connector? All of you have it, right? All of you have USB drives, etc., etc. How many are there? Exactly. It depends on the version of the USB. If it is USB 2.0, which is what is used by most low speed peripherals like keyboards, etc., and many of your thumb drives anyway, it's just 4 wires. Okay, supply, ground, D plus, D minus. We will learn a bit more about it in the last chapter. If it is USB 3.0, the number of connectors is much more. Again, we will leave that for later. Again, HDMI also has a certain number of pins, etc., etc. So the exact connectors, etc., between the controllers and the devices depends on the specific protocol or interface being used. Like USB is a kind of a protocol. Now, in the past, all these used to be separate chips. Every single block in this used to be a separate chip in the past. Let's say 20 years ago. It's no longer the case in the last, especially in the last 10 years, it's no longer the case. All these are getting integrated into one single piece of silicon, at least this much part. And then you call it a system on chip. In the past, it used to be a part of the motherboard. You have motherboard and a lot of chips plugged onto the motherboard. But these days, just one single chip. And that's why if you break open your phone, you will not see that many chips inside, which wasn't the case 20 years ago. And better integration allows lower cost, and it also allows for more reliability. Okay, if you have more chips, you have more connections, so more chances of making mistakes. Now, all these are connected to the processor using some kind of a bus-based mechanism. You can think of bus as some kind of a highway within a country. Okay, like for example, in our case, Pan Island Expressway, which is right in the middle, right? So something similar to that. Most roads connect to that in a way. But in reality, it is usually multi-tiered. Just like how a country might have multiple expressways. So there is high-speed bus, which connects high-speed devices like RAM, flash, etc., etc. And there is usually a separate low-speed bus, which is used to connect relatively lower speed devices like sensors, etc. So high-speed devices are RAM, flash, graphics cards, etc., etc. And there is usually some kind of a connector between the two buses, the high-speed to low-speed bridge. Just think of it as a road which joins two expressways. Now, LPC 1769 is a system on chip. It consists of an ARM Cortex M3 processor, which is the processor of the system. Then there is RAM, flash, system timer, etc. GPIO, UART, SPI, I2C, all integrated into one single chip. Now, we will look at all these in the second half, in this half of the module, in more detail. We will also look at the interrupt controller. So in the first half, you mainly focused on this and this. Okay, the rest are in this half. Now, there are three categories of peripherals. Now, what is a peripheral? In a computer system, anything other than the processor is in some sense a peripheral. So, there are some peripherals which are considered very, very core to the functionality of the system, and which is there in every system which is based on ARM Cortex M3. Those are what we call core peripherals. And example for core peripherals are your interrupt controller, your system timer, etc. These are very closely associated with the Cortex M3. And irrespective of the manufacturer, all Cortex M3 chips will have these peripherals. It is designed by ARM. Okay, but there are several system on chips based on ARM Cortex M3 processors, like those from ST Microelectronics, then NXP, Texas Instruments, and so on. But all of them will have a system timer, an interrupt controller, etc. So those are so-called core peripherals, and they are designed by ARM. Other companies will buy the whole design using, including the processor, interrupt controller, system timer, etc. Then fit other peripherals around it to make it into a complete system. So this much part is designed by ARM. and everything else within the system on chip is by NXP. So this is by ARM and this is by NXP. So what NXP did is it bought this part and designed other peripherals around it and made it into a chip. So these two are considered core peripherals. Now, everything which is on the same chip, that is which is a part of LPC 1769, which are not core peripherals, are called on-chip peripherals because they are on the same chip, but they are not considered core, and they are designed by NXP. So core peripherals. Now, these core peripherals are connected to other peripherals on the baseboard when you plug in your LPC 1769 board onto the baseboard. It will make some connections onto the board, right? Because you have some 80 odd pins sticking out, which will go into the so-called board, baseboard. And there are a bunch of peripherals on the baseboard like light sensor, accelerometer, you have your OLED display and switches, LEDs, etc. These are all what we call external peripherals or baseboard peripherals. So there are three categories of peripherals. Okay, and understanding this is very important. And who designed this? Each of these peripherals is designed by a different company, but it was all put together into one single baseboard by the manufacturer of the baseboard, which is Embedded Artists. Now, how can the processor interact with all these peripherals? It is using a bunch of so-called peripheral registers. So the software interacts with hardware by reading or writing peripheral registers. So any interaction between processor and another hardware happens through reading or writing peripheral registers within that hardware. And these peripheral registers should not be confused with your normal processor registers like R0, R1, etc. These are outside the processor. So how does the processor access them? They are accessed just like how processor accesses memory using load and store. Load and store, if you use assembly language, if you are using C language, you will use pointers because you need to hold an address. To be able to read or write a location, you need to know the address, right? You need to access the location through its address. And the variable which holds an address in C language is pointers. And that is what makes C language special. And that's why every single operating system in existence right now is written in C language or a variant of it. Okay, whether it is Linux, Windows, Mac OS, you name it, it all has some, not some, it is all mostly written in C, if not entirely. Okay, so the idea is you access peripheral registers just like how you access memory. Now, there are three types of peripheral registers. Status registers, which is to check the current status of the hardware. The status could be, for example, whether a particular communication has finished or not, whether it's ongoing or not, etc., etc. Then there are control registers, which are written by the processor to give command or control signals. Status registers are read by the processor because the processor asks another device for the status. Okay, what is the situation right now? Whereas control registers are for processor to give commands to a device. And then we have data registers, which are read by the processor or written by the processor to do actual data transfer. So if the processor wants to send a lot of data to another device, okay, so the processor will keep writing to the data register of that device. So that's the idea. So 3 types of registers. So imagine a situation where, you know, you are asking someone to do something. Okay. So you are asking your friend to do something. So you will tell the friend, please do it for me. That is like giving a command or control. And then later you might ask the friend, hey, are you done with it? And that is by checking the status. And sometimes your friend might ask like, oh, in order for me to proceed, I need this particular information. Can you give it to me? And then you give that information through data registers. So that's the idea. Got it? So each peripheral will have a bunch of data registers, control registers, and status registers, one or more, which you read or write to interact with that particular peripheral. Okay, so the processor or the software running inside the processor will do the reading or writing, and that's how the processor talks to the hardware. Now, can you give me an example for some peripheral registers that you have seen so far? Any peripheral register that you have seen so far? FIO set, FIO clear, FIO pin, FIO mask, all of them are peripheral registers. Even your pin cell is also a peripheral register. Now, next question is, we are able to read or write these registers, right, by using their addresses. The addresses could be shared with the memory, or it might not be shared with the memory. So depending on that, we have 2 types of addressing schemes: memory mapped input output or port mapped input output. I will explain. So in memory mapped scheme, the addresses for peripheral registers share the address space with the memory. So what do you mean by sharing an address space? What exactly is an address space? Address space is nothing but a range of addresses. Okay, let's say I have addresses from 00 to, let's say, FF. I can say that this forms an address space. How many bits? It's an 8-bit address space, right? Because I am having 2 hexadecimal characters, 8 bits. Now, if the address space is getting divided between memory and peripherals, like for example, if I say this much is used for memory and the rest of the addresses are used for peripheral registers, then the scheme is memory mapped input output. So let's say 00 to 0F is for memory, and from 10 to FF is for peripherals. So the address 10 will correspond to a particular peripheral within a particular hardware, and let's say F0 could correspond to another register, possibly within another hardware. So you allocate addresses to each peripheral, and if the addresses allocated are in the same memory space shared with your memory, then you call it memory mapped input output. And then the way you access these peripheral registers is just like how you access memory using load and store. So that is called memory mapped input output. And that means you cannot have 2 locations, one in the memory and one within an input output device having the same address. You cannot have. Address clashes are not okay. Because once you do a load or store, once you send a particular address, it should be addressing a unique location, right? There shouldn't be a confusion. So you cannot have the same address within 2 separate devices. Whereas there is another scheme called port mapped input output, where the memory and peripherals are in separate address spaces, which means, let's say your memory has an address space of let's say 002 FF. The peripherals can also have an address space of let's say 002 let's say 0F. But then there is a clash, right? There is a scenario where the same address belongs to two different locations. So how will you discriminate or differentiate between the two? So in port mapped input output, you typically have some separate buses for input output and memory. There is a separate set of connectors. Here you can see it's the same set of connectors. So when the processor sends an address, it goes to both, right? Whereas here, the processor can decide to send the address through memory bus or input output bus. So there won't be any confusion because the same address will not go to both the devices at the same time, even though the addresses could be the same. Okay. So how will the processor decide whether to send it through the memory bus or input output bus? It's based on the instructions used. There are separate instructions for accessing memory and input output in computer systems following port mapped input output. An example would be Intel. In Intel, there are separate instructions for memory access and for input output. So there is something equivalent to load and store for memory access, but there are separate in-out instructions for accessing peripherals or input output devices. Got the idea? But this scheme is kind of out of fashion right now. There are advantages and disadvantages for both. You can think about it and we can discuss later if need be, but I'm not going into details. But memory mapped input output is much more popular right now. That also has some challenges associated with it, but like I said, let's not get there. Now, how do we really access these peripherals in practice? Do you really use load and store to read or write these peripheral registers? Because eventually that's how you can access peripherals, right? Hardware. In order to talk to a hardware, you should be able to read or write registers within the hardware using some kind of load and store. But do you really do it that way these days? Eventually, yeah, but when you write your code, you don't really go down to that level. What you do is just make use of what others have done, right? Reinventing the wheel is no longer considered a good idea. So what we do is use libraries. So just call some library functions and they will do it for you. Just something like GPIO set value something. Then it will allow you to set the GPIO value directly without really having to worry about which register within the GPIO peripheral should I be writing to or reading to, etc., etc. So all those dirty details or complexities are hidden from the user by a nicely packaged function like GPIO set value. And a collection of such functions associated with a particular peripheral is called driver functions, and a collection of driver functions is typically what you call an API, or sometimes a collection of driver functions is what you call an API. So it encapsulates the process of reading or writing peripheral registers. And they internally use pointers to access peripheral registers because eventually you will still need to read or write those registers, right? They are done using pointers. And it allows ease of programming. So it provides you a higher level of abstraction. So it is much easier for you to get started with your project. And it also allows portability. So if let's say you wrote a program for a particular system, you want to take the program to a newer system and run it on that system. If you are hard coding every detail yourself, you will have to make substantial changes before you can let it run on a new system. However, if you are using easier to use functions, you might be able to recompile your code for the new system without any changes if you write it in a nice way using functions and libraries. You only need to change the library. Unfortunately, in many cases, libraries are provided by the manufacturers. Like if you have done Arduino programming, which many of you have done, right? Actually, all of you have done. What did you do? Just call some easy to use functions, and then things are done for you, right? Like digital write, digital read. It's just one line and you are getting a lot of things done. So if you take it to a new platform, the exact way in which the digital write or digital read, etc. are implemented will have to change. But someone will do it for you, so you will have an easier time. Your main program might not even need to change. That's the idea. There are three main libraries that we are going to use in this module. Very important because people get confused all the time between these libraries. One is libcmsys, which contains helper functions for core peripherals, such as NVIC, interrupt, systic, etc. Then you have libmcu, which contains helper functions for on-chip peripherals, and libA baseboard for external peripherals. So remember, there are three categories of peripherals. One is a core peripheral, which is systic, interrupt controller, etc. And all the helper functions can be found in libcmsys. And then you have libmcu, which contains helper functions for on-chip peripherals, which are not considered core, but which is a part of the chip, the system on chip, such as PinCell, GPIO, I2C, etc., etc. And then we have libA baseboard, which is for accessing peripherals on the baseboard, like your light sensor, temperature sensor, accelerometer, OLED display, etc. Okay, so remember this hierarchy. Now, before we get started with I2C, let us go through some distinction between some categories of protocols. Now, what exactly is a protocol? A protocol is like a language which has to be understood by two parties so that they can communicate with each other. Just like how I am talking to you in English, because that's a language which I can speak and you can understand, right? If I start speaking in my own native language, I don't think anyone in this class will understand. So the point is, the two devices will have to agree on certain set of standards so that they can understand each other. Good idea, right? And these standards could be in the form of voltage levels, timing information, the sequence of bits, and the meaning of bits, etc., etc. Okay, so all these have to be agreed upon for the two devices to talk to each other. And these standards are sometimes simply called standards or interfaces or protocols, etc., etc. All these are pretty much the same. Now, depending on the number of wires used and depending on how the data is sent, you can divide them into parallel or serial protocols. In parallel protocols, you use a certain number of parallel wires to transmit bits in parallel. Like for example, if you want to send 8 bits of information, you can have 8 wires connected between the two devices. So all the 8 bits are sent in parallel. This is as opposed to a serial protocol where you might have only one wire and all the 8 bits are sent through the same wire, but it cannot be at the same time, right? So you send one or the first bit, wait for some time, and then the second bit, wait for some time, send the third bit, and so on. So bits are sent one after the other. one after the other is also called serial, right? So serial interfaces. So which one do you think is better? Yeah, at least some of you are in my tutorial class. As an engineer, the question for which one is better should always be answered with depends. Because you can almost always find a scenario where A is better than B, right? If A is absolutely better than B, B wouldn't even have existed in the first place, correct? So the argument, I mean, it depends on the argument, it depends on the scenario, the correct answer. When your speed requirement is very high and the distance is very, very short, then parallel protocols are usually better. Whereas if your distance exceeds a few centimeters, parallel protocols are no longer good. Why is it so? Any idea? Sorry? Yeah, one argument is yes, parallel protocols would mean you will require more wires, right? More wires would require more space on the board, more number of pins for the peripherals, etc., etc. Yeah, that's a good argument. Any other problem with parallel protocols? Yeah, there will be timing issues. So parallel protocol suffers from something called a bus skew. Different signals travel at different speeds through the parallel wires. All these parallel wires might not have the exact same length, and they might be subject to different inductances, capacitances, resistances, etc., etc. So the speeds at which they allow signals to travel might be different. And at high speeds, even small difference in timing would cause a lot of issues. And this problem is what we call a bus skew. Like for example, see, at this point, all these 3 bits are changed at the same time. But at the receiving side, you can see this B3 came much later than, let's say, B1 and B2. So the original data that you send is 110, right? And here the time for which 110 is valid is this narrow time. Got some idea? And this is due to differential speeds at which signals travel on the wires. Okay, I am just giving you a very simplistic view. In reality, things are a bit more complicated. Once you take the module, if you take this module on electromagnetics, you might understand things a bit better. Anyway, for now, I'll just leave it there. And it also suffers from crosstalk. Different signals from different wires interfere with each other. These wires, in order to maintain consistency, have to be close to each other, right? Because to make sure that the lengths, etc., are the same, they should be relatively close to each other. But if you make it close to each other, they will start affecting each other because of inductive or capacitive coupling. Because any two metal conductors next to each other will have capacitance, right? And higher frequencies are usually conducted by capacitor, right? Or by, a capacitor will allow the higher frequencies to pass through, which will cause them to affect each other. And same goes for inductance. Any two conductors will have some inductive coupling between them because of the interaction of their magnetic fields, right? So because of all this, you will have your signals getting corrupted, which is avoided by serial because there is only one wire. The next distinction between protocols is synchronous versus asynchronous. What is synchronous? Heard of it before? Synchronous means anything which uses a clock. The two devices talking to each other will use a clock along with data in synchronous schemes. In asynchronous schemes, you will send only data and no clock. So which one do you think is better? Yeah, good. Again, for short distances, we generally tend to prefer synchronous protocols because having the clock will make it easy for us to know when to sample. Because you can look at the edge of the clock and figure out when to make sense of the data we are receiving. So we get both clock and data, look at the edge of the clock, and then decide, okay, now I should look at the data, now I should look at the data, and so on. So the timing information is obtained from the clock. So synchronous protocols are generally simpler and faster, provided the distance is short. What will happen when the distance is long? Yeah, they will have the same problem similar to that of parallel protocols. Because in some sense, the clock and data are sent in parallel. They can affect each other and they can go off timing, right? And what happens if the clock and data are not correlated in time? In the sense, what will happen if the time correspondence between your clock and data is gone? Yeah, then having the clock is more harmful than useful in a way, right? Which would you prefer? Not having a watch or a watch which tells you the wrong time? You might as well have the first option, right? Not have a watch. At least you are not misguided. Yeah, same thing goes here. So when the distance is longer, you wouldn't prefer synchronous. And that is where you will have asynchronous protocols, where you only transmit the data. The receiving party will look at the edges of the data itself and try to make sense of when to sample the data. And detecting the edge of the data and deriving timing information from them or from the edges is challenging with respect to hardware, and that's why asynchronous protocols are usually more hardware intensive. But they are pretty much the only option if you are transmitting data over long distance, because you cannot trust clock if your distance is too long. Got it? I'm not going into exact details. I'm leaving it as an exercise for you to read up. Maybe we can take a 5 minutes break and continue at 3:08.